Okay, so I hope the quiz went well for all of you. We are going to continue on with some material today. This is dealing with linear approximation and differentials. Just to kind of give you outline of where we're at, you've got 3 more sections in chapter 4, including the linear approximation and differentials, before we'll have our next exam. So we should be looking probably in probably 2 weeks, we'll have our third exam, which as a side note is the last exam before the final exam for the semester. So linear approximation and differentials is actually one of my favorite sections, and the reason is because my research was in linear approximation when I did my dissertation. Alright, so let's look at, sorry about that, my email is open right now. I'm going to just close it out here so I don't keep getting those little noises saying that I've got email. So linear approximation here is, as it is we're trying to approximate something. And let's just give an example of a problem here of what we want to maybe be able to do with linear approximation. So for example, let's look at the square root. Of course, we know what the square root of 1 is. That's just 1. We also know what the square root of 4 is. That's just 2, because those are easy to do. Now, let's look at here, for instance, the square root of 1.1. Now, I know we could do this on our calculator and get the number. But how do we actually get that number? Like, how does your calculator come up with that number? Well, there's lots of ways that you can come up with this number. Good morning. And one of the ways you can come up with this number is something called linear approximation. So let's go ahead and look at what this is. So we're going to use linear approximation to try and figure out what the square root of 1.1 is. So first off, we're going to go back just to our definition of a derivative, but we're going to use the alternate definition. So the alternate definition, remember, was f prime at a is equal to the limit as x approaches a of f at x minus f at a over x minus a. So this is where we're going to start with, and all we're going to do is say, I'm just going to say, well, I want to cross out this limit. I don't want to have to do the limit. But if I cross out that limit, I can no longer say that it's equal, because it's not equal anymore. But what could I say? Well, I could say that f prime at a is approximately f at x minus f at a over x minus a. Now what we're going to do here is we're going to solve this for f at x. And so solving this for f at x, you'd have f prime at a times x minus a is approximately f at x minus f at a. And then solving it, we'd get then that f at x is approximately, you'd have positive f at a plus f prime at a times x minus a. And in reality, we've just done all of the work, and we've actually come up with the linear approximation. Right here, this, and I don't know why my pen did that weird jump there, this right here is our linear approximation. Now, this concept is so important that the textbook gives us another name. They call this L at x, and L for linear. So L at x is equal to f at a plus f prime, man, my pen is acting weird this morning, f prime at a times x minus a. So when you see L at x, it's just because the book, and I agree with the book, that this is just such an important quantity here that we give it its own special name. We call it linear approximation, and we call it L at x. So before we actually use this in an example, I want to kind of illustrate what's going on here. And we're going to illustrate this with the graph of the square root of x, because that's what we're looking at. My marker keeps doing a weird, like, little heartbeat thing there. Okay. So I'm going to just graph square root of x, which square root of x we know looks like this, roughly. And then I'm not going to worry too much about being super accurate, but I'm going to put 1 here, because that's the one we're going to do. And of course, we know that at 1 it's equal to 1. But what I'm going to do is I'm going to draw a tangent line here. So this is my tangent line. I'm going to redraw that tangent line. It doesn't look very tangenty to me now that I see it. There, that's a little bit better. So my tangent line. Now I'm going to, this isn't going to be the scale, I'm going to exaggerate here. I'm going to say, well, we're trying to find the square root of 1.1. So I'm going to say 1.1 is right here. And if 1.1 is right there, this, of course, here, this is the exact value. But then what we're doing when we're doing a linear approximation is essentially we're using this tangent line. So this is our linear approximation to the square root of 1.1. So of course we have some error. Our linear approximation isn't 100% correct. There's some error involved with that, and that distance there is shown in the green. Now I've exaggerated the scale on this just so that we can clearly see this here. But let's go ahead and see how we would use this equation to get that approximation, and then we'll see how good that approximation actually is as well. So we want to approximate the square root of 1.1. And we're going to say here using a equals 1. And in this equation here, I'm going to write the approximation down again. L at x is equal to f at a plus f prime at a times x minus a. You will always be given a. And we sometimes refer to a as the center. So if we do this here, what do we get here? Well, first off, my function is simply just the square root of x. A is equal to 1, because the problem states it. And then we're trying to find L at 1.1, because we're trying to approximate the square root of 1.1. So in this formula here, we need several things. We need to know what f at a is. We need to know what f prime at a is. And then we also have to do a couple other computations. Well, f at a, I'll just write it over here in red. F at a is easy. F at a is just f at 1, which is just the square root of 1, which is 1. And then f prime, well, we need to know what f prime at x is. And f prime at x would be 1 over 2 square root of x. And that's just taking the first derivative. Of course, if you don't see that right away, I'll put it off to the side here. Remember that f at x is x to the 1/2 and f prime at x would be 1/2 x to the negative 1/2, which is 1/2 square root of x. And so of course then we just need to find what f prime at a is. So f prime at a would be f prime at 1, which is equal to 1/2 square root of 1, which is 1/2. And so then we have I'm ready to figure out my linear approximation. So linear approximation at 1.1 would be f at a, so it's 1 plus f prime at a, which is 1/2, and then x is 1.1, my a is 1. So I have 1 plus 1/2 times 1.1 minus 1. So this is equal to 1 plus 1/2 times 0.1, which if we do that, we get 1.05. So what we're saying here is that the square root of 1.1 is approximately 1.05. Now, if we wanted to figure out the exact value, of course we could use our calculator, and I'm pulling up my calculator real quickly here. And the calculator gives me 1.048808848, and then of course it's going on forever. So we can see that of course this isn't 100% correct, but if we were to round this to 2 decimal places, our approximation is actually exactly the same as what the actual value of the square root of 1.1 is. So we're going to end this video here. We're going to do a little bit more, another example or two with the linear approximation in the next video.